Hi everybody, and welcome to the next video on vectors. In this video we kick the dimension up one level and we talk about two-dimensional vectors, otherwise known as tables, otherwise known as matrices, otherwise known as arrays. So those are all essentially synonymous. I try to use the word table as often as I can just to distinguish from the single dimensional vector lists we've been doing already, but I may sometimes say matrix or array. It all means the same thing in this context. So in this video we will discuss a vector of vectors. So that's what a table is. If you look at this table here, it consists of two vectors, right? This is a vector, it's a list, as is this. So you can think of a table as a list of lists. So I have a first list, a second list, maybe a third, fourth, fifth list, etc. So this video focuses on taking our single dimensional vectors and letting the dimension go up by one, and now we're living in a two-dimensional place, and so we get a table. Here is how you create an M by N table. And notice, of course, in two dimensions, you have to specify a number of rows and a number of columns. So M here denotes the number of rows, N is the number of columns. So here you have 2 rows, 3 columns, for example. Okay, so here's what that declaration looks like. It's a vector of vectors. So that's why you got vector and then vector there. So you're saying I'm going to create a list of lists, and the data type is whatever it is. You can have int, float, string, bool, whatever right there. You then give your table a name. You then say the number of rows, and then you have to say vector int again, or vector bool again, whatever your data type is, and then give the number of columns in parentheses like this. So just for example, here is how you declare a 2 by 3 vector of integers. Vector vector int, give it a name. So again, you can just use table or whatever, and you put in a 2 and a 3. So the first thing I should do is apologize for how convoluted this declaration syntax is. And there really is no question that this is sort of a silly kind of syntax here. Clearly, the proper syntax should be something like this. I'm going to create a vector. Here's the data type. I'm going to give it a name. And by the way, there are m rows and n columns. Okay, so notice how much simpler this is than what's currently up here. So even though the syntax should be this, it's not. So you have to take that up with the creators of C++. These are the same people who decided to count at 0, right? Start counting at 0. These are the people who now decide this syntax. If you're dealing with a different programming language, like say Java, then this really is how you would declare a table. You basically just give it a name and give it a number of rows and number of columns, and then you are done with it. But for whatever reason, C++ decides to make things complicated like this. And one of the real drawbacks of this syntax is that if you do this sort of thing here, it's easy to create a 3-dimensional vector also, because you just throw a height dimension on here at the end. You would say m, n, k, where k is the height of this 3-dimensional thing you are looking at. If you want to do a 3-dimensional vector, the syntax gets just ridiculous. You got to do a vector of vectors, okay, and it's just nonsense. So anyway, all of that to say, I apologize for this nonsensical syntax, and we will have to stop at 2 dimensions because 3 dimensions, the syntax is just ridiculous. Okay, so this declaration here, it's doing the same thing that anytime you create a list does. What happens is you create a bunch of boxes. So you create an m by n grid or table of boxes, each of which starts empty. Just like when you declare a normal vector, like what we've been doing, you create a row of empty boxes that you can then fill later if you want to. To access an individual box inside of this table, you use square bracket notation, just like we've done before. It's just that with a vector like we've been doing before, it's just a one-dimensional line of boxes. So to specify the box you want, you just have to name a single position, right? The box at position 5, the box at position 8, whatever. But with a two-dimensional grid, you have to give both a row position and a column position. So that's why there are two parameters here. You have to specify your row and column. Because if all you do is specify, hey, the box at position 5, the computer won't know what you're talking about. Okay, a table is two-dimensional, so you have to give it two pieces of information to locate anything. And yeah, the syntax here is similar to what we had, except now you got to give another number because you're living in a two-dimensional place now. You're searching inside of a matrix now. Okay, so obnoxiously enough, we still continue counting at 0 to start with. Therefore, the first column is column 0. The first row is row 0. So here is how things are laid out. So like 3 right here, this number 3, that's at position 0, 2, even though you might say to yourself, well, it's in row 1 in column 3. So I would think this number right here is at position, this number here is at position 1, 3. Okay, but you were wrong because you start counting at 1, but C++ starts counting at 0. So just for another example here, this 58 looks like it's in row 6 and column 8, but it's not. It's in row 5, column 7. So here, if the name of this matrix is table, then table 57 is the number 58. And so again, this table, this grid, has 100 boxes in it. It's 10 by 10. And so when you create this grid, initially all of these boxes are empty. But I've actually put numbers in here to show a filled-in grid. So somehow you have to fill this out. Okay, so to create this table right here, we could use the following code. We can declare the table first, call it myTable. But again, just like with normal vectors, just like with any variable declaration, this just creates the storage space for things. It doesn't actually put anything in there. So what I've told the computer is, hey, please create for me a 2 by 3 grid of 6 empty boxes. Arranged like this, right? 2 by 3 for a total of 6. If you actually want to put values in there, you have to do something like this. You actually have to fill it in, just like with a regular vector, right? Somehow you have to tell the computer what's happening at each box. So once these 6 lines of code are done, I now have this real life table where each box has a number inside of it. Okay, so by contrast, this little table right here only has 6 entries, so it's not too much trouble to just hard code in all 6 entries. This table right here has 100 entries. So you could say table 00 is 1, table 01 is 2, table 02 is 3, you see, right? You could do this. You could write 100 lines of code. That's highly obnoxious, of course. You don't actually want to do that. And that gets prohibitively time-consuming if I were to make this table even bigger. I could give you a 30 by 30 table, and then you would have to hard code 900 lines of code if that's what you want to do. So to think about how to create this table, I want to just harken back to a homework problem you had. This was in the for loops homework problems. These 2 problems here were priming you for doing things like this with vectors. In particular, these are tables themselves, right? And so to create these 2 tables, you used for loops. What you did was you found a pattern amongst the table itself. And then you use a nested for loop structure where an outer loop had variable I, the inner loop had variable j, and I was keeping track of the row number, and j was keeping track of the column number. So if you've forgotten how that goes, you can just reference the homework code that you turned in, but essentially you will see that what I just described is what you did. So back over here, we also need to think of a pattern that would let us use a nested for loop structure to fill in this table. Because again, a nested for loop structure doesn't take long to write. It's only like 6 lines of code. But if you actually wanted to hard code this, you would have 100 lines of code. So let's think about our pattern here. When we're in row 0, it's just the first 10 numbers, right? And then let's see, row 1, it's just the next 10 numbers, right? So it looks like what's happening in here is that in table I, the numbers, you could start them with like a 10i. So like in table 1, you have 10 plus something. In row 2, you have 20 plus something. In row 3, you have 30 plus something. So that suggests to me that you might want something like 10i to get yourself into the 30s or 40s or 50s, depending on what I is. And then it looks like you just have to add j, essentially, just add your column number. Although you have to be slightly careful about that because you start counting at 0. But like right here, if we're doing 10i for this row when I is 2, then you could do 10i plus j, essentially is what it looks like, to just increment the number by 1 every time. Okay, so let's see what that looks like. Here's just the declaration of the table. Yeah, okay, so when I is 0 and j is whatever it is, it looks like what we're doing is 10i plus j plus 1. Okay, so let's think about if that makes sense or not. So when I is 0 and j is 0, you're at position 0, 0, and you are doing 10 times 0 plus 0 plus 1, which is indeed 1. So at the very least, it works for the first entry. Now you can convince yourself it works for all of them by just thinking about what this pattern is saying. It's saying when I'm in row I should first of all do 10 times I, which again makes sense because when I'm in row 5, I'm in the 50s, which is 10 times 5. And then you should add the column number plus 1. That also makes sense because in this row right here, this 50s row, you don't have a 50 right here. So you don't have 10 times 5 plus the column number, because the column number starts at 0. You have the column number plus 1 every time. So in column 1, you got 2's. In column 2, you got 3's. Column 3, you got 4's at the end, etc. So what you should do is take your column number plus 1, and that will get you this sort of thing. So let me just, and by the way, there's one slight issue with this code here. So I'll show you what that issue is when I do this. So let's make sure this all goes okay otherwise. So vector int, I gotta do all this nonsense, right, where it's sort of, this is unnecessarily long to do here. Okay, so now I've created a 10 by 10. And so, whoops, let's fill it in as I've done here. Okay. Whoops, you certainly can't use the same variable twice. It will not like that. And I'm sorry, I misspoke a second ago. There's actually no problem with this code. What we want to do, though, is make sure that the vector is being filled in properly. And so to do that, we have to print this vector to the screen. So in a second, I will show you the code to print this to the screen. And so I was mixing up this code with the code that prints it, is why I said there was an error. But there's no problem here. Okay, so again, let's just convince ourselves by looking at an example, this is okay. When I is 3 and j is 4, so we're right here, 3, 4. We're supposed to do 10 times I, which is 30, plus 4j, right? J is 4 plus 1, which is 35. So it looks like it'll be all right. So to check that it worked all right, let's think about how you would print a two-dimensional vector to the screen. We're going to mimic what we did with one-dimensional vectors. So what did we do? We just started at position 0, went up to the size of the vector, and printed what was at that position. So if you want to mimic that, I suppose what you would do is start at the first position, which now is 0, 0. And then what you would have to do is just print the first row, then print the next row, then print the next row, etc. And so to do that, you need some sort of nested for loop structure that says, hey, when I is 0, when I'm in row 0, I want j's to increment by 1. So I want the columns to start at 0, then 1, then 2, then 3, then 4, etc. But you keep your row the same the whole time. And then when you up your row to 1, you would again increment all the column numbers by 1 while keeping this one fixed, etc. And so the for loop structure that does that for you is like this. So for int I equals 0, I less than m, because I is keeping track of row numbers, you increment I by 1. And then for int j equals 0, j less than n, where j here is keeping track of column location, so that's why we go up to n, you will print the entry at that spot inside of this j for loop. So again, let's think about I being 0. When I is 0, we go into this global for loop. The first thing we do is encounter this inner for loop, and in this inner for loop, we create a new variable j, and j goes from 0 to n. But while j is doing that, whoop, okay. Sorry, I didn't mean to look up what 0 was. But anyway, so while j is doing this, while j is going from 0 to 1 to 2 to 3, etc., I is 0 that whole time. And so when j is done, we print a new line, and then we come back up to the global loop, and now I is 1. And when I is 1, the first thing we do is go to this inner for loop, and then the j's run from 0 to n again, etc. And then we print a new line when we're done with that. So this nested for loop structure really does print row by row by row. And so I'll confirm that for you in a second. I should point out, though, that there are, of course, other ways you could print a table. You could maybe print column by column by column if you want to, if you wanted to think about how that would look. But I think the easiest way to do the printing is this, row by row by row. So just like this for loop will work to print any one-dimensional vector, where, again, normally we didn't know what the size was, so you would just put myvec.size here, whatever. In the two-dimensional vector case, this nested for loop structure will always work. You don't have to worry about modifying this. No matter what your table is, as long as you have the correct m and correct n here for the rows and columns, that will always work. So let's print this one. So in this case, my row and column numbers are the same. It's a 10 by 10. So I want to just make sure this works properly. J++. Whoops, I should say 4. Okay, and then I'm going to print my table at position ij. And I'll put spaces in between each of those individual entries, and then when I'm done printing a row, I will print a new line. Okay, it doesn't like j equals 0. Why is that? Oops, parenthesis there. Okay. There we go. Okay, so again, this just creates 10 by 10 empty boxes. This fills those boxes in. This will show us what's in those boxes. So this nested for loop structure is actually what's going to show us what's in there. And looky there, it does print the correct table. So it was supposed to go, 1 through 10, 11 through 20, all the way up to 91 through 100. So of course there are some issues with this printing here. It's not displayed particularly nicely because of the different number of digits, but we can talk later about how you print things to the screen in a more aesthetically pleasing way when dealing with these tables. Okay, so that is the end of this video. You should really just take a couple of things away from this introduction to tables, how to create them, and in general, creating something big like this will require you to find a pattern like this in terms of I and j. So that could be easy, it could be hard. It depends on how complicated this table is. So you should be able to create tables, and then you should be able to print them to the screen. So those are the two takeaways from this video. So in class, you will get practice doing those two things.